Okay, so the problem we are trying to solve here is we have a projectile, the green ball on the left, and you can control the speed, set the speed, and you can specify the launch angle. And our goal is to hit the target, the yellow block on this gray cylinder. Okay, so clearly this um, yellow box has x coordinate and z coordinate, z being upwards, and we want to ensure that this projectile hits that. So this is what is known as the initial value problem, because we set the initial conditions and then just see what it does. And this is a good candidate for optimization. Okay, so for this particular uh, problem, I have created a new template called template_projectile, which is in tiny.cc MuJoCo. So you'll the same thing. We'll download that, rename it to projectile_opt, and then make those 3 changes, which we always do. And then we'll go to projectile_opt and type ./run_Unix. So if everything works fine, then you should just, I believe, see a projectile being launched. Okay, let's do that. So here I've already unzipped. Well, I think I've downloaded the projectile template. Okay, don't need this. I can call that projectile_. Okay, so within here, let's make those 3 changes. Okay, so let's close this and this. And so we have to rename this to projectile_opt. That's change number 1. Second one is the make file. We need to change this to projectile_opt. And then the last change is in the Unix. So projectile_opt. So if everything works right, then we should get this up and going. So cd projectile_opt. Okay, so the ball drops. Okay. I believe I set the initial speed, and that's why it is launched and it drops. Let me just check this quickly. Should be here somewhere. Yeah, I set the initial speed in the x direction and initial speed in the z direction. So that's why it was launched. Let me just quickly check something. Let me just put 0 and 0. See where the ball is positioned. It goes nowhere. Okay, it's on the ground, right? That's good. Okay, so what we'll do is I'm going to modify the ball.xml file. Now, my goal here is to create that cylinder, place it at a distance, and then put a block on top of it. And once I have that block, we're then ready to try the optimization. Okay, so let's start by creating the cylinder. And what I'm going to do is I'm going to make the cylinder the part of the world body, so it will not move. Okay, in order to do that, I just have to specify it here in your plane. So jump type equals cylinder. We need to put it somewhere. So let's just put it at x distance of say 5 units. So I know that my ball is at 0, 0. So I'm going to put it at 5, 0. And then I need to specify the center of where I want to put the center of the cylinder. Now, let's say the cylinder is of height 2 meters, in which case I need to put the center of mass at 1 meter above the ground, and size equals, let's make it quite big, 0.2 for the radius, and 1. I need to say 1 because now it will be of length 2 meters, and then I need to give it some color. 0.9, 0.9, 0.9, 1 is gray. Okay, let's quickly check this. Okay, there it is, standing on the right side. Looks good. Okay, now let's, and by the way, it does not have any joint, so it's fixed to the ground. It's not going to move because it's not connected to the world through a joint. I also want to create a cylinder, a box, and that box should be free to move because I eventually want to hit that box with the green ball so that it flies in the air. So what I'll do is I'll create a body tag. And then let's see. So this is going to be position equals, okay, now this is sitting right on top of that cylinder. So its x coordinate has to be 0, y coordinate is 0, same like that, but it has to be on top of the cylinder. Now, what I think I'll do is I'll make a block of, I don't know, maybe size of, maybe height of 0.1 or something like that. So what I need to do is I need to put it at 2.1 because its height is, that's the center of mass or the geometric center of the box is 0.1 meters. And so it has to be 0.1 meters above the topmost point of the cylinder, which is at 2 meters. So that's why it's 2.1. And now I need to respect that 0.1. So when I create the box, I'll create it such that such that it is exactly 0.1 in half the length and half the height and width. So type equal to box size equals 0.1, 0.1, 0.1. RGBA equals 0.9, 0.9, 0, 1. Okay, I think that will work. Let me run this. Okay, there you can see the boxes right there. Yeah, I think we are all set. It's not fun. Okay, so we are all set with the XML. Let's go to main.c and let me just try to launch it randomly. So let's say 10. This is for the X, and then I need to also go. It also needs to fly up. So this is just trying to guess an initial condition. Okay, in case it did not. So I've set it up so that the camera moves with the center of the ball, so it always keeps the ball in the middle. But you can change that if you don't want it to show that. So we can, so you can see that it didn't really make it there. So we can maybe, it needs to be launched a little bit faster, maybe 8. Okay, that was too high. And you can just play with this and see if it works. And you could basically solve this way too. I just missed. Okay, so we're probably very close. But anyway, we will not use our guesswork to solve this, but use the optimization. Okay, so I got that. Okay, so now let's get back to what we are trying to achieve here. Okay, so as I said, we have the ball, which we can specify the, well, in this case, I specified the x and z velocity, but you can also specify a v and theta, and then the x velocity is v cosine and z velocity v sine. And I think it's better to parameterize it with v theta than the x, vx, and vz. Okay, so we'll do that. Second thing is once we launch it, we saw that it ends up hitting the floor, and that point when it hits the floor is x and z end. And in order to hit the target, we want x and z end to be at x target, z target. That's when the ball will hit the cube. So what we'll do first is, before we can actually solve this and hand it to optimization, we need to create a function which, given a set of inputs, will produce the right outputs which we care about. So the inputs in this case are going to be v, theta, and the third one, which probably people don't sometimes put in the optimization, but I think this makes it much easier to do the optimization, is the time of flight. Even though time of flight is, time of flight just depends on v and theta and the location of the target, including the time of flight in this particular example actually makes the optimization easier to optimize and solve. So those are my inputs, and the outputs are going to be the end position of the projectile after that time of flight, so x and z. Once we have this, I will show you how we can put this within the optimization framework and optimize for v theta and time of flight such that x end, y end, actually should be not y, but z end equals x target, z target. Okay, so let's create this function and we'll test it within the init controller. Okay, so we are creating this function and I'll do this in here. This is a good place because once I have the initial condition, I just have to launch that ball with that initial condition. So I'm going to create a function and let me just call it simulator. It'll have inputs x in, it will produce an x out. And I've already decided that x in should be 3 dimensions. I need to give some initial values. So v theta and time of flight, and I need to specify them. So that is my input. The output is something which the simulator would calculate after integrating the equations. So that, let's say I initialize to 0. Now I need to specify these things. V, let me give some random value, say 10, and then theta as, this is an angle, so let's say it is 45 degrees, which is pi 3.14 divided by 45, sorry, 4, and then time of flight equals, I don't know, 2 seconds. Okay, now this function has not been written, so let's write this down. All it does is takes in this input and produces the output, which is the end position of the projectile after integrating over time of flight seconds. So let's create this void time of flight double x in, inputs are 3, outputs are 2. Let's pull out v theta time of flight from this. So v equals x in 3, sorry, x in 0, theta equals x in 1, and time of flight equals x in 2. So I got that. Now what I need to do is put that in the simulation and then simulate for time of flight second. So this is where we can look what we have done in the past, which is the main block which simulates ahead in for t seconds is this thing called MJ step. So this basically simulates from the given initial condition, which we specify using this. It simulates over, it simulates till this while loop is done. So it simulates for those many seconds. So we can maybe take inspiration from this and use this kind of code here. So I'm going to copy this, go back to init controller, sorry, simulator, and copy it, never mind. So while something is true, MJ step, M and D, and then I need to set the initial condition here. So T, Q, well, 0. This is the X component of the velocity, and we know it's V times cosine of theta, and then D, Q, well, in the Z direction, which is 2, equals V times sine of theta. And so given this initial condition, this will integrate till D time, that's the variable within MuJoCo which keeps track of time, is less than, or this should be a negation, so it should be greater than time of flight. Okay, so how do we check this? Well, we can just make it printf, %f, new line. We want to print the position. So let's say that we want to figure out what the position is after this integration. So we just do q pos 0 for the x position, t BQ pause 2 for the Z position, sorry, Z position after time of flight. So let's run this. Time of flight, time. Okay, is there? Don't seem to notice there. What's there? Undeclared identifier. Oh, that must be here. Okay, so that's not important, but it's 0 and 0.1, and that's because after 2 seconds it was on the floor. And remember, the height is 0.1, so that 0.1 makes sense, but the 0 doesn't quite make sense to me, because that just means that it never really traveled anywhere. So there's something which is incorrect here. Did it even integrate? Let's see. Oh, it did not even integrate. Why is that? Is it well this? Yeah, this is my bad. This shouldn't be. So if it's less than time of flight, then you want to do this, and if it's greater, then you need to execute. So I just incorrectly put that condition in the while loop. Okay, so you can see that integrate up to 2 seconds, and after 2 seconds, the X position was 12 and the Y position, Z position was 0.1. And that 0.1 just 0.01 just means that it is on the ground. Okay, because it has to, because that's the radius of the ball. Okay, so this code is working. I just need to do this change, which is I need to produce X out, which is 0 equals the same thing, BQ post X out 1 equals Q post 2. Okay, so now I have a function ready. It basically takes in the X in input, produces, sets the initial velocity and direction, and then integrates over time of flight and gives me the output. Now, one thing you'll notice is, let's say I did this, right? Let me just take this code and come back to my, so remember how this goes. There's a main loop which runs. In the main loop, I first, right here, initialize the controller. So that sets the initial conditions. And then it goes through this MJ step to integrate the equations till the end time. Let me just put this here, right? So put it in right here after init controller. You'll see that when you run this, it just gave 212.01.1, which means that now I'm starting my simulation with this initial condition. And that's not what I want. I want it to start from fresh, right? I want to do the calculations in init controller. I want to compute what the initial conditions is and then set it to whatever I want to set in the velocity. So this is, looks like it's just continuing its integration right here. That is, it's once the time is 2, it just keeps integrating from 2 onwards over here. So we don't want that to happen. So what is done in this case is we want to basically reset the simulation. We want to set the simulation to set it back to time t equals 0. And that is done by a function called MJ reset data. So here's what I'll do. Right in the simulator, after we do our computations, we just want to reset the simulation. So MJ reset data, M and D. Okay, so M is, remember, keeps the model, D keeps the data. It'll flush everything in the data. It'll put it back into the initial state, which we specified in the ball.xml. Right? So now if we run the same code, let's see what we get for this printf. Okay, so you see it's 0, 0.1. That's because it went back to the origin. So this is how you can reset the simulation as many times as you want. So you can do computations, reset it, and do some more computations and so on. Okay, so that reset it. And then if you want to, for example, set the initial condition, you can set it here. Okay, so I think we have the function all set. Okay, now since we have the function all set, we can now go to the next step of, no, before that, let me just do one thing, and I think that'll be helpful. So since this function, I'm later going to convert that to an optimization kind of, where it'll call the optimizer. I want to take X out from this and then set it. So I do X out, then I want to, so right here, after, what I'll do is I'll optimize. Okay, I won't use the simulator, but I'll optimize. The simulator will go somewhere else, and I'll reset the whole thing, and then I'll reset the velocity right here. So once I set the velocity here, it'll automatically be ready for my MJ step in the main loop. So it'll be X out, V equals X out 0, theta equals X out, sorry, X in, X in. Maybe this is so confusing. Let me just skip this for now. I'll come back to it. I'll have to do it over here later on, but maybe you'll understand the continuity when I come back to it a little bit later. Let me just do this later on. So now what I'm going to do is, let's try to set up the optimization problem. Okay, so what our problem is, we want the ball to hit a target, right? So in this case, we are not really optimizing anything. So what we can do is we can just set the cost to 0. Okay, we're optimizing nothing, that is. We're going to subject it to some kind of bounds. So velocity and theta has some bounds. So velocity can be infinity, but theta, we only want it to limit to 90 degrees because otherwise it fly backwards. And then time can be from 0.1 to infinity. Now, in general, the smaller the bounds are, the better is a chance of getting an optimal solution. If you can do that, try to do that. Don't keep the bounds so big. Here I've put 0.1 because t cannot be negative. And if you put t equals 0, then there's going to be problems with integrations. I never really advise putting a lower bound of 0, even though lower bound of 0 is perfectly acceptable for t and, well, t, not for t, but theta, yes, you can have that lower bound, right? And then our constraints are x end should be x target and z end should be z target. So what I'm going to do is I'm going to put this equations inside NLOpt and then optimize it. That's my goal. And for this, as I've shown you, I need to set the cost to 0, and I need to set both these constraints. So I only need to use the equality constraint. Okay, so I'm going to show you how I do optimization, which is basically start from something which works and then slowly modify it so that it basically solves the problem you care about. What I've done in this case is I've put constraint.c within projectile underscore opt. Okay, so you don't have to do anything to copy it. The first thing I'll do is I'll include constraint.c within the main file, so it'll be able to call the functions within constraint.c. The easiest way to do that is to go right up and here constraint.c. Okay, so this way everything in constraint.c is included part of main.c. Now let's open constraint.c. Okay, this is exactly how I wrote it earlier. I'm just going to delete this unnecessary things. Okay, the first thing I do is we are trying to integrate this code with our code. And the first thing is to just get this optimization software to work with our code. So I cannot have two main files within my program. I believe it'll give an error, but so let me just change the name of this main. Let me call it optimize IC or initial conditions. And then just take this, save it, and call it within init controller. So if everything works right, then it will call this and then it'll print the same output we got when we ran constraint.c. So let's run this. So nothing will happen as expected, but it did print the same thing. And this is just a check I do to ensure that I'm able to integrate one code with another code. So once we have this going, now it's a matter of us modifying this constraint function to suit our purpose. Okay, so let's do that next. Okay, so first of all, let's see where we want this ball to hit. What is our target? So remember, I set the ball to be here, 5, 0, 2.1. Now everything here is planar. I'm not going to set any y velocity, so I'm only interested in x and z target. So my x target is 5 and z target is 2.1. And since everything is taken care in the constraint.c, that's where my optimization is. I'm just going to create a global variable there and use that. You could also make a local variable, but let's just make a global variable. Double x target equals 5. Double z target equals 2.1. Okay, so we've got the target. Now, the next thing to do is, I think we are better off not having the simulator here, because the optimization is not done here, but it's done there. Now, it'll actually work if you have the simulator here function, but just to make it more readable, I recommend putting all this code which does anything to do with optimization in that files constraint.c. So I'm going to move this simulator from here to there. And the easiest way to do this is probably to move the simulator function block. So let's take this block and move it here. Okay, nothing changed. If you want to check this block, we can check that quickly. Let's not run optimize, but run simulator x in, x out. I think, well, yeah. So now if you run this, it should just work just fine. Oh, error. Okay, so the error here is that it doesn't really have any idea of these variable m and d. So we remember we've used in the simulator, we've used m and d, but it has no clue about those because constraint.c was added here and then it was included here. It did not know anything about these things which were defined later. So one way to fix this issue is to define these up here before constraint.c, and it'll take care of that. That's one way. The other way to take care of this is to pretty much define this as an external variable. So let's do this second route. So let's define these as extern. That makes the code aware that I've defined them somewhere else in the code. Okay. So now let's see if that runs. Okay, I think I have not commented out the first one. I have two definitions of simulator. I don't need a simulator here anymore. So let me just delete it. So get rid of this and run. Should work fine. Okay, nothing will move because it's not really set to move, but it basically was able to compile. So I've got the simulator right here. And okay, what is strange is, okay, the printf is my bad. The printf is right here. So if you want to check it, you could take the printf. Let's take this printf and put it right here. So that way we can check if this simulator produced the right output. The reason why the simulator produced 001.1 was because I reset it before I printed it. So let me just do that. And if everything looks right, then it should print 212.0. So it now works. The simulator is successfully ported to constraint.c. Okay, so we've got that working. And I think it's time to move to formulating the problem in NLOpt. Okay, so for that, what we'll do is as follows. Let's go to constraint.c. Okay, now we're going to change this file and make it such that it is specifying this problem and not the problem which I have programmed it to solve. Okay, so what we'll do is we'll just get rid of all, there are no parameters, we don't even need that. So just get rid of that. So I got rid of the parameters here. Let me look at the cost. There's no parameters, so comment this. We don't have these things. Comment. we said our cost is simply 0. So just everything goes, just the cost equals 0 remains. Inequality, same thing. We don't have this. We don't need these things. Okay. Now the input to this is x, as shown here. The x is giving me the variables which are being optimized, the decision variables. The decision variables are basically x in, v, theta, and time of flight. So what I need to do is I need to call the simulator here. The simulator has inputs of x in and output is x out. So my x in is x, so I just keep it as it is, and then x out is my output, and then I'll need to define x out, so that way it's ready. So now x out comes back with the values for the x end and z end, x and z end. So what I need to do is I need to collect that x and z end and then set that equal to x target, z target. So all that needs to happen here is I need to say x, so you can just do it in 2 steps. Double x n equals x out 0, z end equals x out 1, and then of course x end minus x target, and I've already specified target as a global variable, and then z end minus z. Okay, so that takes care of these constraints. Okay, and the cost is taken care of. Let's move on. Look at inequality. We don't have any. Comment it out. Okay, now we've defined the main block of the optimization. So the number of decision variables are 3. That is v, theta, and time of flight. So 3. The constraints are 2. That stays as it is. We don't have inequalities. So comment it out. Our bounds are, as you saw here, it's 0.1 for the lower, and then upper bound is infinity for the first and the third one, and then 90 degrees for the middle one. So 0.1. And this will be, I think huge value is defined to be some big value. I don't know what exactly it is. And then this should be 3.14 divided by 2. That's 90 degrees. But let's just make it slightly less than 90 degrees, minus 0.1. And then we have huge. Okay, those are the bounds. The bounds are taken care of. Cost is taken care of, and this is taken care of. The only thing now needs to be done is to make this last part of the code work for us. Lower bounds, upper bounds. We don't have any costs. So now, since there is no cost data, the change you have to make here is we need to pass null, no parameters. So we need to make that third argument null. This specifies the constraints on the equalities. So we want them to be -8, or you don't have to be so high, can be less precise. Okay, -4. Comment out these. Since this is the data, it should be null. We're not passing parameters. No inequality. Comment it out. Right here, we got to give some initial conditions. So now our initial conditions are, well, let's see. We can actually, specify initial conditions, or we can just pass them through optimize. So why don't we do that? So what it'll mean is we can just pass some x in, whatever we think is a good initial guess. So instead of initializing them here, we're initializing the init controller in main.c, and it'll go here. That might be a cleaner way to do it. So let's do that. So then x is not there, it just is x in. Okay, now in this case, there are three decision variables. So I put 3, and then the output is, the cost is minf is 0, it's going to print 0. So let's get rid of these 2. And then since there's no x, I redefine that to be x in. This will be x in. Okay, I just need to work on this last part. I passed x in as the input argument. So I need to go main.c. And here, this will be my input. Okay. So what I would like to do now is, this is my initial guess, which is 10 to 45 degrees to. It goes in x in. It optimizes. Out comes x in with the optimized value. So I want to maybe print them. So printf. Yeah, I made many changes. Let's hope it works. Otherwise, I'll need to debug it. Okay, so it says found minimum 10, 0.7852. I have no idea if it actually found the optimal value because it didn't do anything. And that did not do anything because after I got these values, I did not set the initial condition. Let me just set the initial condition now. So v equals x in 0, theta equals x in 1. Now I need to integrate to a certain time. What I did was in this basic code, it basically runs for a certain time. And the time I actually specified here, the simulation ends when for 10 seconds. So instead of simulating for 10 seconds, I only want to simulate for the time of flight. So what I'm going to do is go back here, init controller, and let's first define the time of flight is x in 2. So I need to make sim be time of flight. Okay, that takes care of that global variable. That's the time of flight. I need to set the initial condition for the velocity. So v2 and d equals v cosine v theta, time of flight. And once I do this, it's all set for the next step. I see an issue with this. Let's see what happens. Okay, no one did not hit. The problem I noticed is that this is not the right way of resetting it. So what's happening here is it's going to optimize. It's optimizing IC, so it's going to the simulator. It's doing this integration, but once it does the integration and it computes the x and z end, it's integrating from that x and z end because I've not really reset the simulation. So the mistake I made here is this should not be here. Well, you could put it here, but you also want another reset right here. So once it computes all these things, I need to reset it. Okay, so it cleans up everything and then it does the next step. I think this might work. Let's see. Okay, so it just stopped before it could finish. So what I'm going to do is I'm going to increase the time. So let's go to simend. It's in main.c. And then let's integrate for, this is just to check it. So let's do another 2 seconds. Okay, it hit. Okay, now here it's not really disposing the block. That's because I think I've specified the default masses, which are heavy, and so it really does not dislodge it. So let me just change the mass of the ball, and that might help. I believe I can do it right here. So make the mass equal to 1. So it's a heavy ball, and then mass of this equals 0.1. Okay, see if that works. No. Okay. Make it lighter. Okay, I know what the problem is. It's not that the problem is that, it's because the box is fixed to the world. I've not really specified a joint, so it cannot move. So I need to actually take this and put it here. That's just making the box free to move in any direction. Now I should probably get dislodged. There it is. Okay, it looks fun to watch. Just getting it right. Okay, so that's one. Now, there's one other thing you can do with this. That is, we specified a cost of 0, but what if we try to minimize the time? So let's just change the optimization cost to be minimize the time, in addition to all the constraints we've satisfied. Okay, so that's just a small change. So if you go to constraint.c, I need to change the cost. I just need this to be time. Now, here's the thing. This is very specific to NLOpt. There is a simulator. I've called it in equality, but then if I want to do some computations, not time, but something else, I need to integrate. So should I call simulator again here? Right? Just makes sense for me to call the simulator again here. And it'll do the computation, then I can use this, should be a function of the simulator state, right? Now, unfortunately, the developer of this software didn't really think of this condition where you don't, well, in this case, you just repeat the computations twice, which is a problem, right? Why would you repeat computations twice, especially when you have some very lengthy calculations and you're doing things real time? So there is no real provisions in the software to write a function or a modality where you can combine the cost and the constraints, that you're only calling it once and not twice like I would in this case. There are tricks to get past it. There are ways in which you keep a track of the recent most variable, or the decision variable. So you sort of cache it, and then you check that the current value with the cached value, if it's the same, then you run the simulator. So you don't run the simulator. If it's changed, then you run the simulator. And so that's the way people fix these things. What I'm going to do is what I know about this simulator, this optimization, is that the cost is called before the equality constraints in this optimizer. And so if in this software, if you want to do anything, what you want to do is you want to specify your simulator or whatever calculations once in the cost, and then define global variables which will let it be accessed to by the equality or the inequality constraints. So what that means is, what we need to do is we basically take this thing and put it here because we want to call it in the cost. Now our cost is essentially the end time, right? So D, or time of flight, could also be X3 or X2, sorry. Okay, that's our cost. We did the simulations, but what about X and Z end? So what I'm going to do is the following. I'm just going to set X end and Z end to be X out 0, X out 0 and X out 1. That way, I'm already setting the value for X and Z end using the simulator. Here, I don't do anything, okay? But that will create a problem because X end and Z end not been defined. So here is what I do. I create global variables. X end, double Z end. So this is how it works. Since I've defined these global variables, they are initialized. Then the optimizer calls my cost. It runs the simulator. It computes X out 0, X out 1. It is initializing X end to Z end to the right value. And since the equality constraint is called after my cost, it has already been set to the right value. That is the value which is obtained by integrating the equations or using the simulator. So what I was able to do is, by defining global variables, I was able to not call the simulator twice. I was only able to call the simulator once in my cost, and use those values in equality constraint. Okay, so this is sort of saving you some function evaluations or simulator evaluations by doing it. Okay, so now before we actually check this, let me just go back and put 0 here and see if my optimization still works, and then I change it to that cost. I forgot a ending bracket. Sorry, it's a semicolon. It still works. Now let's just change it to time x to which is time. Okay, it was pretty fast. It actually chose a crazy fast value to hit the block. Can I slow it down? Probably not. Yeah, it's just launched. There it is. We can check it this way. I don't know how to slow down this. It's 5 seconds. So it stays. Yeah, that is crazy fast. Let's zoom out here. Can dot. Okay, let's change this, and then view. We can go back off here. So I think that would be go back would be 20. Yeah, that was pretty fast. 30. Yeah, I didn't expect it to be so fast. Okay, so that's pretty much it. That's how you can do these optimizations with NLOpt. Let's do.